In this video, I'm going to answer one question. How do we actually program a quantum computer? To do this, we're going to have to take a tour through computer science and physics. First, we'll look at how coding works on classical computers, so that we have a baseline for comparisons. Then, I'll talk about compilers, the software on classical computers that translates your code into computer language. Next, I'll talk about what this computer language actually is. This involves the binary ones and zeros that you often see in movie hacking scenes. Then, we'll shift over to quantum computers. I'll explain quantum mechanics, superposition, and entanglement using them to build up quantum logic gates. These logic gates are the operations that we actually use to act on qubits. Then lastly, I'll discuss a specific problem for quantum computers. Oh, also, this is part one of a two-part series, since I don't want this video to be too long. I'll actually code the problem on IBM's quantum computers in the next video. Anyways, to understand how to program a quantum computer, you must first understand how to program a classical computer. Lots of you probably already know about the programming languages like Python, C++, Java, and others, but if you don't, it doesn't matter. These are programming languages that allow us to interface with computers by typing in things that are more or less similar to human languages. By typing a specific set of commands and then running the resultant code-containing file, you can make your computer execute those commands. For example, this is some code that I had ChatGPT write because I'm too lazy that counts to 10. What you may not know is that the programming language that you type is not actually what the computer runs. A compiler is a special program that converts programming language into machine language. Different languages have different compilers, and each is a translator for that specific programming language. The way that compilers do this is pretty complicated and beyond the scope of this video. So we can just think of them as black boxes that take human written code as an input and output machine code. Machine code is the actual code for your specific program that a computer runs, a sequence of ones and zeros that tell the individual bits in the CPU how to operate. Importantly, here I want to remind everyone that to the computer, everything is ones and zeros. The text on your screen, the operating system, the YouTube window that you're using to watch this video, everything is ones and zeros. The reason that I'm drawing a contrast here between the regular ones and zeros that the computer sees and the specific ones that the compiler translates is because the computer can't run the program that you write from the sequence of ones and zeros that display what you wrote on the screen. The computer needs to translate that sequence of ones and zeros into an actionable sequence of ones and zeros that it can use, and that's what the compiler does. But how does this machine code work? Machine code is a set of instructions that tell the computer about the specific bits to operate on. It contains ones and zeros which, when read by a computer, can be interpreted as direct instructions as to where it should send electrical signals. The way that these operations are physically carried out is with logic gates. Logic gates are the fundamental building blocks of classical computers, and work by taking electrical signals as inputs and giving different signals as outputs based on the inputs they receive. These are actual physical circuits made up of bits. For example, an AND gate can be constructed which only lets current flow if both of the wires that go into it have current flowing, meaning that both of the inputs are ones. There are other operations that we can make other than AND, and we can chain these logic gates together to make more complicated circuits, which can add and subtract numbers and bus information around to other bits. Once we can add, subtract, and transfer information around our computer, we have all the building blocks necessary to run programs. So to recap, the code that we write as humans is translated by a compiler or some other program into machine code. This machine code is run on the processor, where it instructs the computer to do a specific series of mathematical operations using logic gates. These circuits execute the actual computation by modifying individual bits inside the computer and create an output performing all of the instructions in the code. Now that we know how classical computers work, we can talk about quantum computers. Quantum computers are also coded with high-level coding programming languages like IBM's Qiskit. These programming languages are run on classical computers, compiled on classical computers, and then finally executed on quantum hardware. I'm going to build up our intuition about programming quantum computers from the opposite way that I talked about classical computers. When I talked about classical computers, I talked about the high-level code first, then the compiler, and then the machine code, and then the bits. For quantum computers, since it's hard to have an intuition for a type of computer that does not exist at scale yet, I'll first talk about the building blocks, the individual bits, and the circuits. The first of these building blocks are the principles of superposition and entanglement from quantum mechanics. Before I get into explaining quantum mechanics, first let's define a system in physics. A system is just what physicists decide to analyze with math. Usually, we treat systems as isolated from the environment because considering all interactions with surroundings makes the math impossible. For instance, in high school physics, we often ignore air resistance because it's too complicated, and it doesn't really significantly impact the results of our calculation. Physicists choose what's vital based on its impact on the outcome. Now, a quantum system is a physical system following the laws of quantum mechanics. Typically, it's extremely cold or very small with some exceptions. Examples include electrons in hydrogen atom orbitals, electrons in superconductors, and ions, which are charged atoms trapped in an electric field. In quantum mechanics, superposition is where a given quantum system has some probability of being in multiple states at the same time, and it is not known even to the particle itself until a measurement is carried out. These states could be energy, spin, angular momentum, or some other important physical quality. It really doesn't matter, and different types of qubits use different properties depending on what works best for the case of that system. Once measurement occurs, the superposition collapses, and the particle is forced into a definite state. The probability with which a particle collapses into a given state in the superposition is dictated by the mathematical coefficients in front of each state in the superposition. Just square the coefficients to get the expected probability that will measure the system in that state. Now, the reason that this collapse happens is a hotly debated philosophical topic that's outside the scope of this video. But it turns out that whatever your interpretation of quantum mechanics is, it doesn't actually change the way a quantum computer's algorithms work. So we'll worry about that in another video. Entanglement is another quantum phenomenon that is useful in quantum computers. When two or more quantum systems are entangled, measurement of the state of one system directly and immediately informs the state of the other. Before you ask, no, this does not allow for faster than light communication. A simple example of an entangled state is a Bell state. In this Bell state, we have a state with two quantum particles. There are four possible combinations of the two bits, 00, 01, 10, and 11. However, in this Bell state, we've prepared it such that there's a 50% chance of 00 and a 50% chance of 11. The other two states have no probability and will not be measured. In reality, on a noisy quantum computer, they'll be measured a very small amount. But the point is that if we measure 0 in the first qubit, then we are guaranteed to measure 0 in the second qubit. If we measure 1 in the first qubit, then we're guaranteed to measure 1 in the second qubit. So the state is entangled. Anyways, we can combine superposition and entanglement in quantum algorithms to solve problems. The way to do this is not obvious and is completely different depending on the type of problem you're solving, in the same way that solving different problems on classical computers requires different code. But how do we actually implement these algorithms? For simplicity's sake, because they're the most concrete example to explain, I'm going to talk about how to implement programs on neutral atom quantum computers. That said, the general process will be similar for all types of quantum computers, with the main difference being in the interaction between software and hardware, meaning the physical way in which we implement the quantum logic gates. Importantly, the concepts of superposition and entanglement can be applied to any type of quantum computer, whether it's neutral atoms, superconducting qubits, spin qubits, trapped ions, or any others. I'm talking about neutral atoms here for concreteness, but I could be talking about any type of quantum computer, and the only thing that changes is how to physically implement the logic gates. Similarly to the classical logic gates, a quantum logic gate is just an operation that takes a qubit in a given state and changes it in some known and repeatable way. We can do these gates on 1 or 2 qubits. Think classically we had the NOT gate, which flips a single bit, and the AND gate, which takes 2 bits as inputs and only returns 1 if both of the inputs are 1. In neutral atom qubits, instead of making circuits like with classical bits, these quantum logic gates are implemented by shooting lasers at the individual atoms. In different hardware implementations, this is the step that changes. For superconducting qubits, for example, instead of shooting a laser, we'd apply some specific current. Anyways, by shooting a laser at a specific frequency or color at our qubits, we can change the state of our qubit. How do we know what frequency or what color to use? Well, that comes down to knowing the frequency of the transition between the 0 and the 1 state. If we know the transition frequency, then we can do some math to calculate the frequency we need to drive at with a laser. The actual frequency we drive at depends on the specific logic gate that we want to apply. Okay, So now that we can implement single qubit quantum gates, we can make a small leap to multiple qubit quantum gates. These are still logic gates, except instead of putting our individual qubits into a superposition, they entangle them. These are the quantum analogs to classical 2-bit operations like AND. One major difference, however, is that in a quantum computer, all of our logic gates must have the same number of inputs and outputs. This is different from classical computers, where an AND gate has 2 inputs and 1 output. There's actually a deep physical meaning for this that has to do with the reversibility of quantum computers, but I'll do a separate video on that. In different qubit platforms, multi-qubit gates are implemented in different ways, but usually it's done by forcing some known interaction between 2 qubits. In our neutral atom system, usually that involves promoting one of our atoms to a Rydberg state. This is a high energy state, with the electron far away from the nucleus. This charge separation between the positive nucleus and the negative electron creates a dipole moment, which is an electric field that is generated when charges are separated from one another. This dipole moment electric field interacts with nearby atoms, preventing them from entering a Rydberg state. Since the state of our high-energy atom now dictates what states the other atoms can be in, they have now become entangled. Entanglement in other systems looks quite different, but often it involves making the 2 qubits interact one another by some mechanism. This is a major reason that in quantum computing, 2-qubit gates are significantly more difficult to implement than single-qubit gates, because forcing the qubits to interact with one another naturally means that they can also interact with their environment and lose information. Okay, so now that we know a bit about superposition and entanglement, how do we actually program a quantum computer? Well, since we can build quantum logic gates, we can run an algorithm by stringing these together. This is the equivalent of machine code for quantum computers. It's the individual sequence of logic gates to be applied to our quantum bits in order to carry out our computation. Often, sequences of quantum logic gates are referred to as a circuit. While talking about individual logic gates is useful for education and for hardware research, in the real world we would never program a classical computer directly with logic gates. Instead, we code with programming languages. Similarly, for quantum computers, we do the same thing. We make quantum programming languages as an abstraction, which need to be translated into machine code the same way as classical computers. But it's also significantly easier to think in terms of code than in terms of what's happening to the individual bits. So let's go to one of these programming languages and see what it's like. One major difference is apparent right away. Classical computers are programmed on, well, classical computers. When you want to write code to run on your MacBook or your Lenovo, you write the code on that machine and then run it on the same machine. Quantum computers, on the other hand, are not coded directly on the quantum computer. Instead, we use classical computers to interface with them. We do this for 2 reasons. One, because quantum computers are currently not powerful enough to run any type of user interface, so the alternative is to do it by hand. And 2, classical computers are already perfectly good for writing and compiling code, so there's no reason to reinvent the wheel here. Coding a quantum computer starts off very similar to coding a classical computer. We load up a notebook and we write some code in our favorite quantum computing coding language. I'm going to use Qiskit, which is IBM's coding library for quantum computers, which is written in Python. We can write some code in the notebook. Here, I'm just going to write some random, mostly useless code to show you how it works, and then we can run that code. When we run the code, it compiles as it's running and translates the code from human language into a series of quantum logic gates, which need to be applied to our qubits. These logic gates are interpreted by a classical computer, which triggers the actual quantum hardware to fire the specific laser pulses that correspond to the desired gates. This is the step where the algorithm is actually run on the quantum computer. Finally, the result is measured and we get our answer. Now that we've gone through the general process, let's try working through an actual example. I'm going to use a toy problem. Toy problems are problems that aren't super useful for anything in the real world, but they're good teaching examples because they demonstrate how a system works. In this case, this toy problem shows how a quantum computer works very well, so it's a great teaching example. The algorithm is called the Deutsch algorithm, which is the simplest version of the Deutsch-Jozsa algorithm. Now, to be clear, the Deutsch-Jozsa algorithm is also not useful, but the Deutsch algorithm is the simplest case and it's easiest to show for a teaching example. When I actually code up the algorithm in Qiskit for the second video, I'll code the Deutsch-Jozsa version, but for now we're going to work with the simplest case. Here's the problem we want to solve. Imagine we have a function, let's call it f, on a configuration of 2 bits, such that it is either 1, constant, meaning all configurations are mapped to the same value, or 2, balanced, exactly half of the configurations map to 1 and the other half map to 0. We know advanced that our function is one of these two categories, but we don't know which. Let's think first about the most efficient way to do this problem using a classical computer. Usually, the way we think about this is to ask ourselves, what is the worst case scenario when I run a given algorithm? This is because code is often reused, so you're likely to run into this worst case scenario at some point. The worst possible scenario for our classical algorithm would be where the function is balanced, but also where the first two outputs that are recorded are both 0 or both 1, meaning that the function looks like it's constant at first. Thus, for us to be absolutely 100% sure whether our function is constant or balanced, we need to evaluate 3 of the inputs. This means that we need to run the function 3 times. Since we're coding a general solution and we don't know how this function will work, we always have to prepare for this worst case scenario. Now what about the quantum case? It turns out that in the quantum case, we can get away with running the function only once. But first, we have to understand what it means to even operate with this function on our qubits, and to do that, I need to explain some notation. In quantum computing, we use bracket notation. We do this because it's super useful shorthand and prevents us from having to write long, complicated math functions to describe the physical state that we are in. Bracket notation is really just a way to disguise linear algebra. A bra is a row vector and a ket is a column vector. The gate operations, like the Hadamard gate and the NOT gate that I was talking about before, are actually matrices. Now, if you don't know linear algebra, you don't really need to know what this means, because one of the conveniences of bracket notation is that for some quantum computing stuff, you can kind of just sweep this under the rug, and that's what I'm going to do in this case. Anyways, just think of things in terms of the 2 bit states, 0 and 1. When we apply our function to an input configuration AB, we map the general state AB to the state A, B plus f of A. Here, the B plus f of A is modulo 2, meaning that the result is divided by 2, which can only be 0 or 1. The first step of our algorithm is to prepare 2 qubits in 0 and 1 respectively. We then apply the Hadamard gate to both qubits. I'll show what the mapping is for the Hadamard gate here below. The Hadamard gate maps 0 to 0 plus 1 over root 2, and 1 to 0 minus 1 over root 2. Anyways, we get the following result. So, by applying it individually to each qubit, we've actually put our quantum computer into a superposition of all possible answers. We can see this by just distributing out all of the terms using the distributive property. So, we have 0, 0, 1, 0, 0, 1, and 1, 1. The second step is function evaluation. We operate the function on our second qubit. This is just done with a gate the same way the Hadamard gate or other gates are applied. Now, I won't tell you how the function is implemented because I don't know. Not because I don't understand how function implementation works, but we're doing this for a general case. In reality, this function could be any constant or balanced function, and so I can't tell you a specific implementation because telling you that also tells you the function. Remember, we're just trying to do this for a general case, so we don't want to be specific here. Anyways, if we apply the function to our second qubit, this takes our state to the following algebraic mess. Okay, don't worry, I'm going to explain what this means. Here, we can do some casework to get a better sense for what's going on. If f of 0 is 1, then we get the following, where our first term picks up a relative minus sign. If f of 0 is 0, then nothing happens. So, we can rewrite the state as follows to express this in some more compact math notation. This equation says the exact same thing as the equation before, only now we've re-expressed it. By doing a little bit more algebra, we get to the following state. Since we haven't done any 2-qubit operations, the second qubit is not entangled with the first qubit. And actually, the second qubit isn't really important anymore, so we can forget about it. This superposition depends on the outputs of f. If we measure our quantum computer, we get the following. If f is constant, then f of 0 equals f of 1. It doesn't matter whether they're both 1 or 0, just that the values are the same. So let's take f of 0 equals f of 1 equals 1 for our example. If this is the case, then our equation becomes the following. The other term vanishes because 1 minus 1 equals 0. If f is balanced, then f of 0 does not equal f of 1, and we get opposite values. By similar reasoning, we can equally show that we only measure 1. Notice again, this algorithm doesn't actually care about how the function f ever works. It only cares that the function satisfied our criteria, meaning that the function was either constant or balanced. One more thing I just want to add in. Usually entanglement is generated inside the function f, so we won't explicitly see it, but you can get entangled states. Alright, so that was the 2-qubit case of the Deutsch-Jozsa algorithm, which is called the Deutsch algorithm. In the next video, I'm going to actually implement the Deutsch-Jozsa algorithm in Qiskit and show you how to program it on a real quantum computer. Until then, this video is getting long and editing is hard, so like I said, I'm breaking this up into 2 parts. Until next time, I've been Lucas, this has been Lucas's Lab, and thanks for watching.